AIKatz is an attack that targets generative AI desktop applications.
This attack operates on a post-compromise basis. After an actor achieves execution on a machine, they can access a user's generative AI conversations by harvesting credentials from the local desktop applications.
The threat model assumes an actor has code execution on the target machine with the user's privileges. The objective is to extract authentication tokens from applications like ChatGPT or Copilot to impersonate the user and access their conversation history.
The technique is effective against multiple AI applications because of a shared architectural foundation.
Applications such as ChatGPT and Claude are built on the Electron framework, and Microsoft 365 Copilot uses WebView 2. Both of these frameworks are based on Chromium, which means this shared foundation can be targeted by a single attack technique.
The attack vector is related to Chromium's process architecture. When an application starts, a main process launches. This main process then spawns multiple worker processes for functions like networking and storage. These processes communicate with each other using the Mojo IPC framework.
The worker processes have different memory access restrictions. The memory of the storage worker process is blocked, but the memory of the network worker process is accessible. This permissive memory access for the network worker enables a credential extraction.
The extraction process itself involves scanning the process memory for specific authentication artifacts.
The technique is to scan the memory of the application's network worker process, searching for patterns that match authentication tokens or session cookies. Because these applications are dedicated to a single service, any tokens found this way are expected to be the target credentials.
For both ChatGPT and Microsoft 365 Copilot, the target is a JSON Web Token. The JWT header is a constant for the application, so an actor can scan the process memory for its specific base64 encoded pattern.
Claude, on the other hand, uses a session key cookie that has a static prefix, skant. An actor can scan the process memory for this prefix to locate and extract the full session key.
Once an actor has the authentication token, several follow-on actions become possible.
A captured credential enables a range of post-exploitation activities. These include data leakage by downloading chat histories, denial of service by deleting chats, and prompt injection to tamper with the AI's behavior. The access could also be used for lateral movement.
These actions map to specific tactics in the MITRE Atlas framework, including OS credential dumping, use alternate authentication material, and manipulate user LLM chat history.
The implementation of the attack can vary based on application-specific constraints and the bypasses needed to overcome them.
In both ChatGPT and Claude, messages are stored in a tree structure, not a simple chronological list. Each new message references the ID of its parent message. This structure constrains direct prompt injection. When an actor injects a prompt using the API, the desktop client is unaware. So the user's next message simply references the previous parent message ID, which overwrites the injected prompt. To bypass this, an actor can inject a prompt that creates a persistent LLM memory. The injection message itself is then overwritten, but the LLM memory persists, making the injection's effects durable.
Microsoft 365 Copilot is constrained to business contexts and may disengage from conversations it identifies as being outside this scope. Therefore, injected prompts must be crafted to appear as legitimate business queries for the injection to succeed.
While the memory scanning technique operates within a single user session, a different vector can cross the user security boundary.
The potential for escalation beyond a single user session exists through an alternate attack vector, DLL path injection.
The Claude application presents a vector for this escalation. Its process tries to load a specific Intel graphics driver DLL that does not exist. The operating system then searches for this DLL in all folders listed in the system's path variable. An actor can place a malicious DLL with the correct name in one of these path directories, which the Claude application will then load and execute.
If a directory in the path variable is a shared multi-user location, this technique crosses a user security boundary. An unprivileged user can place the malicious DLL there. Then, when a privileged user runs the Claude application, the malicious code executes with that user's elevated permissions, creating a privilege escalation vector.